All right, welcome to another lovely day of differential equations. Today, our plan is to attack higher order differential equations. Basically, look at what do we do when we have third derivatives or fourth derivatives or fifth derivatives or whatever order nth derivatives. Um, and I think you're going to like this. I think you're going to like today because you already know how to do this stuff. You'll see. But before I go into that, let me open it up to you guys. Any questions about the homeworks or anything we've been talking about that you'd like to discuss? All right, I'm not hearing anything. I'm not seeing anything, which makes me think we are good to go ahead and move forward. All right, well, uh, so here we go. Let's talk about higher order differential equations. Now, these are exactly what they sound like. These are just going to be ones that instead of having just a second derivative, right, and first derivative and all that, we're going to allow ourselves to have up to nth order derivatives. So first and foremost, we're going to continue just talking about the linear ones. And for linear higher order, these are going to be the ones that can be written in this form, where we'll have the nth derivative plus some function times the n minus 1th derivative plus a whole bunch of things here. And then finally a piece of n of x times y, and that's going to equal f of x. So this is exactly the same kind of thing that we did before, except when we did second orders, you know, we wrote them as like p and q. I don't want to do that because I'm going to run out of letters potentially. So instead, we'll just call them P1, P2, P3, P4, and so on down to Pn. But all these P's, these are just functions. They are going to be functions of x. They could just be scalars too, right? They could be constants. They could be 2, 4, you know, stuff like that. So those could be constants as well. But they're going to be functions, and they're going to be multiplying on our y's. And so anything that can be written in this form is a linear nth order differential equation. And that's what we're going to concentrate on, mostly because that's what we've been concentrating on even with second order. Like, think about this. Have we done any second order differential equations that weren't linear? Because first order we did, right? We had the ones that were separable and, you know, had some other forms, you know, like the exact and stuff like that. But when we got to second order, we've just been targeting the linear, and so this is really kind of a natural progression. There are techniques to deal with nonlinear, but that's beyond the scope of this class. And if you take more math later, more classes that are specifically about differential equations, you'll see that. Anyway, so these guys are going to be linear. Now, here's what's kind of cool. If we think back to, you know, how do we know if we've got solutions and all that sort of thing, you may recall that there was a way to tell if we had unique solutions. And do you remember what it was? Like if I gave you an initial value problem.
Abel's theorem, right?
Okay, so we had, yeah, it's pronounced Abel's theorem, but yeah, so Abel's theorem, where we could look at the Wronskian, and the Wronskian would tell us whether or not we had a unique solution. And do you remember what had to be true about the P and the Q in
They
that
needed to
case?
be continuous.
Yeah, they need to be continuous. Okay, so for this, for the higher order, we actually still have both of those things. We still have Abel's theorem, and we have the fact that we know that we're going to get a unique solution and I'm going to put here to the initial value problem because that's what we need to get a unique solution. But unique solution to the initial value problem exists if the p sub I of x are all continuous. And yeah, this is a little shorthand because of course we know it had to be continuous on an interval that contained the point where we were, you know, our initial value and blah, 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 blah. But you know what I mean here. Okay. So this is not new at all. And in fact, the reason that this has to be true is the same reason that we saw when we were doing those for the second order. So it naturally just follows. Like our conditions for the second order weren't specific to second order. So we know we're going to get a unique solution if they're all continuous. We still have the Wronskian, but before we get to the Wronskian, let's talk about the solution to the homogeneous. And solutions to the homogeneous have a fundamental set, just like before. But now it's going to be y1, y2, down to yn. So they're going to be n of them. So like when we did the second order, we found 2, right? For the first order, we found 1. If this is a 10th order, we're going to get 10. So if we go back to the language of linear algebra, the basis to the solution space is a larger dimension, and its dimension is going to be n. But the same thing about these guys, these y1 through yn, they are going to be linearly independent. And so if you find n functions that are linearly independent, they will form a fundamental set of solutions. Right? So anyway, so we're still going to get a fundamental solution the same way. And so we're still going to have the Wronskian. But now for the Wronskian matrix, it's going to look a little bit different. But I bet you can imagine or, you know, think about what it's going to look like. What did we do to build the Wronskian before?
We made a restriction.
Y1 and Y2.
Okay, so we started with y1 and y2, and we did make some restrictions along the way. But what did that matrix end up looking like? So the first row was y1 and y2, and what was the second row?
Y2 prime.
Y prime 1 and Y prime 2.
It was the derivatives. Yeah. So now though, for our Wronskian matrix, we're going to have y1, y2, all the way to yn. So the second row again is going to be their derivatives. So we'll get the y1 prime, the y2 prime, the yn prime. But this matrix needs to be square. So we're going to end up needing n rows as well. So how do you guys think we're going to make the next row?
Second derivative.
Right, that's going to be second derivative, and then third derivative and fourth derivative, until eventually we get to the n-1 derivatives. So we're still going to be able to build the Wronskian like we did before. It's just going to be larger. So when we built that Wronskian, it came from, like Bradley said, we put that restriction on the y1 and the y2. Well, you're going to put a restriction on the y1 through yn, and a y1 prime through yn prime, and y1 double prime to yn double prime. And we're going to keep adding those restrictions because we've got some play since we've got n of these things. And we're going to end up creating this matrix. But it's going to do the exact same thing as before, right? We know that there's going to be a unique solution if the determinant of this is non-zero. right? And that even comes back to the idea of the fact that these things are all, linearly independent and all that. So we're going to build the Wronskian the same way. And like I said, let me go ahead and highlight this with a different color under the unique solution. Right, if we call this the matrix W, we know that there's going to be a unique solution if the determinant is not equal to 0. And we also know that Wronskian is going to actually come from these P's, right? When we do the e to the negative integral business. So it's kind of nice, even though we're in a higher order and all that, we still get the same kind of setup as before. It's just bigger, right? So our solutions, at least to the homogeneous, are going to be some sort of C1y1 plus C2y2 plus all the way down to Cn yn. All right, now that also in itself, though, changes initial value problems a little bit. Because how many initial conditions do we need now?
At least n-1.
Yeah, and actually n-1 isn't quite enough. We're going to need n of them. So think about when we did first order, we always knew y of 0, right? Or y of 4 or something like that. When we did the second orders, we knew the y and the y prime, right? So that was two things. And that kind of extends further here. So let me put a little thing right here for initial value problems. We're going to need n initial conditions. And I think maybe, Victor, where you were saying that n-1 means we're going to have to go to at least the n-1 or n-1st derivative.
Yeah.
So like, yeah, so I think that's maybe what you meant. So if we're going to do a fifth order, we're going to need it all the way down to the fourth derivative. So now these initial value problems are going to be kind of big. There are going to be a lot of constants that we're going to have to solve for, right? Like you look down here, the C1 through Cn. And so there's going to be a lot of information necessary in order to do them. And we'll attack, well, I think we're going to do one initial value problem because I don't want to have to deal with all the algebra and everything for it. So we'll just do the one. Okay, so that's cool. And then if we go to the non-homogeneous, so like what we've got here that I have written where it's equal to f of x, we're still going to create them the same way, where we have to get the solution to the homogeneous. They have the form y equals yp plus, I'm just going to write it as yh. So hopefully you remember when we did this before. We went ahead and we found the homogeneous, but then we had to find a particular solution. We had to find something, any function, that actually worked for this specific problem, right? So this is your particular, and this is your homogeneous. So if we get a non-homogeneous, we're going to actually do it the same way we did before, which is solve the homogeneous, then find a particular. And that finding a particular, you may remember we had a bunch of different options on how to do it. All those options actually are also going to be valid in this case as well. All right, so this page right here, everything that I just wrote here should make you kind of happy because it means we don't have to really learn anything new. We just have to do what we've done before and ratchet it up. We just got to go a little bit harder, make it a little bit bigger, but otherwise we're going to do exactly the same thing. All right, so with that in mind, let's go ahead and do some of this more thing. And I'm going to start just like we did before with the, let's go with linear nth order homogeneous with constant coefficients. So if you go back and you look at second order, those were the first ones we did. Okay, those were the ones where we had the second orders, but everything that was being multiplied to the y prime, the y double prime, the y, they were just numbers. All right, so think about how we did that. What did we do when it was second order?
We looked at it as a polynomial.
Okay, so we created a polynomial, we found the roots of the polynomial, and then what the roots were told us what kind of solution we had, right? So, like, let me give you an example of what I'm talking about. I'm talking about something like y triple prime minus 4y double prime plus y prime plus 6y equals 0, or say the fifth derivative plus 4y triple prime equals 0, or, right? So what we did before was we made a polynomial. Where did those polynomials come from? Do you remember why we even made polynomials to begin with?
I think it was solely for the fact of Abel's theorem.
It was not, actually. It ended up kind of being connected to that theorem, but that wasn't really the reason. Let me remind you, we made a guess. We guessed the form y equals e to the rx or rt. Because if they just have constant coefficients, then something that's exponential could easily cancel itself out and give us 0. And so when we differentiated, y prime, of course, gives us r e to the rx. Y double prime gives us r squared e to the rx. And that's where those polynomials came from, because we could factor out the e to the rx, and that never actually equals 0. So it had to come from the remaining pieces, which was that polynomial. Well, if we go higher order, we're going to do the same thing, because now a third derivative, okay, well, that's going to be r cubed e to the rx. A fourth derivative, that's going to be r to the fourth e to the rx, and so on down the line. And it's going to do exactly the same thing. So this is really good news, because now when you're confronted with something like this, you can just go, oh, I need to find the roots of r cubed minus 4r squared plus r plus 6. Or this other one, I need to find the roots of r to the fifth plus 4r cubed, right? Or ... So it's going to be exactly the same process. Exactly the same. It's just we're going to have bigger polynomials to solve. It also means we're going to have more roots to find. So I don't know if you remember this, but if you've got a polynomial of whatever degree, it has that many roots. Okay, so like a degree 5 polynomial like this one on the bottom, it's going to have 5 roots. The cubic's going to have 3 roots, and so on. That's the fundamental theorem of algebra. So really, we're going to do exactly the same thing. We just have more roots to find. Now, depending on what those roots are, we saw before we got different forms. Well, exact same forms are going to show up. If r is real, right? If it's a real root, we're going to get e to the rx. If it's a complex root, we're going to get the bits with sine and cosine, because that had nothing to do with the degree of the polynomial. It had everything to do with e raised to those powers. And so that doesn't change. repeated roots. What did we do if we had a repeated root?
We use trig functions. No, that was imaginary.
That was for imaginary. Yep.
Just add a variable in front. That
Yeah, we just multiplied. So in this case, it'd be by an x, or we multiplied by a t, right? So we get e to the t and then t e to the t. All right, now here's where things are going to slightly change. When we get to higher order, so bigger polynomial, bigger degree polynomials, there's a greater chance of repetition. And it's possible that we repeat more than just twice, right? Because like think about this one where we're dealing with a 5th degree polynomial. It's possible, not with this one, but it is possible with a 5th degree polynomial that you get the same root 5 times. We could get a pair of complex roots, and then the other 3 could be the same thing repeated 3 times. Right, so there are all kinds of weird combinations we can get. I mean, we could get imaginary roots that are repeated. Now, you just have to be at least degree 4 for that to happen. So really the only catch here is you're going to have more defined, and it's more likely that they are duplicated. Well, if you duplicate a trig one, okay, slap it, multiply by a t or an x. If something is duplicated more than twice, well, the second one gets a, t times, and then the other one gets a t squared. You just continue to multiply as many times as you need with that power. So when we were first talking about this, and I showed you a little chart, and there was something that was like multiply by t to the n, and n is the number of times that it repeats or whatever. When that first came up, that was silly because the only time it ever repeated was with second order, and it was twice, so it was just times t. But that was put there so that when we get here and you go, oh, I got that same root 5 times. Okay, just keep multiplying t until you get 5 linearly independent functions. All right, so really good news.
I have a quick question.
Yeah, go for it.
Suppose we had 3 repeated roots. We would have one that didn't have the multiplier of t, one that did, and then a t squared.
Correct.
Okay.
Yeah, so okay, so let's quit just talking about possibilities or whatever. But let's say this was our polynomial. And I'm just going to give it to you in factored form. Okay. So like, let's say we get r minus 2 cubed times r plus 1 squared times r squared plus 1 to the 4th. Okay, so this came from some differential equation, and this is what that polynomial turned into. Okay, so this first one, we get r equals 2, but it repeats 3 times. So that means we would get solutions of e to the 2t, t e to the 2t, and t squared e to the 2t. So those are the 3 that come from this one. The r plus 1, that gives us r equals -1. That showed up twice. So R4 is going to be e to the minus t, and then Y5 is going to be a t e to the minus t. Now, if we go to this one, the r squared plus 1, that gives us plus or minus I, which would lead to sines and cosines, right? So Y6 would be cosine of t, Y7 would be sine of t, but these are repeated 4 times. So the next set are going to be t cosine of t and t sine of t. The next repeat is going to give us another pair of t squared cosine t, t squared sine of t. And then we're going to get 2 more, which are going to be t cubed cosine of t and t cubed sine of t. So this one would have, this is a dimension 13 solution space. This basis has these 13 functions that form the fundamental set. And if you go back and you look at the degree of this polynomial, r squared to the fourth, that's r to the 8th, plus 2 more is r to the 10th, and then plus 3 more is r to the 13th. So this one's, this would come from a 13th order differential equation. Don't even ask me where you would see something like that in the real world, because I can't even imagine a 13th order. But this is just the process. Every time it's repeated, you just multiply by the next higher power of t, because you need to have something that's linearly independent from the others, right? We're forming a basis. They have to be linearly independent. All right. Now, hopefully this one didn't scare you off, because this is incredibly large. But at least in terms of how we build it, yeah, that's how we build. So let's take these two that I put up here, these two examples, and let's actually run them. Let's see if we can find what their fundamental sets are. And then we'll turn one of them into an initial value problem. We'll turn the second one into an initial value problem, and then go through that as well. Okay, so let's do this. Let's actually solve this differential equation. So it is homogeneous, it does have constant coefficients. So it does lead to the polynomial r cubed minus 4r squared plus r plus 6. So this is going to be part of the challenge. It's going to be finding solutions to these polynomials, because they can get kind of tricky. But this one, I'm just going to help you out. Turns out that this factors to r plus 1 times r minus 3 times r minus 2. I don't know if you remember some of your tricks for these, but one that's really handy is to just like plug in r values, nice numbers, and see if you can get zeros. And nice numbers to try are things that divide evenly into the constant. So in this case, 1, 2, 3, and 6. And the negatives, of course. Because like if you say plugged in 1, you'd see 1 minus 4 plus 1 plus 6 doesn't work. But if you plug in 2, you get 8 minus 16 plus 2 plus 6. That equals 0. So that tells you r minus 2 is a factor. You can divide it out, and then the remaining one you can factor or whatever. But just don't forget those tricks. But anyway, this gives us 3 different r values. So we know our solution then is going to be C1 e to the minus t plus C2 e to the 3t plus C3 e to the 2t. Boom, done. Right, so it's not really that much more difficult. It's just you've got more r's to find. So let's try this other one. So we got a fifth derivative of y plus 4 times y triple prime. But I'm going to make this an initial value problem. So we're going to need to know y of 0. We're going to need to know y prime of 0. We're going to need to know y double prime of 0. We're going to need to know y triple prime of 0. And we're going to need to know the fourth derivative of y at 0. So I just put some numbers here. But this is what this as an initial value problem would look like. So fifth order, we have 5 different conditions. All right, well, let's do it. So this polynomial is going to be r to the fifth plus 4r cubed equals 0, which I can factor out the r cubed. Gives me r cubed times r squared plus 4. So we're going to get r equals 0 and r equals plus or minus 2i. All right. So let's start building our fundamental set. So the r equals 0, what does that give us as a function?
It's just a constant, right?
Yeah, it's just going to be 1. So basically, so C1. But then it repeats. So the next one needs to be T, and then it repeats again. So these are the three that come from the 3 roots of 0. All right, and then the plus or minus 2i, that's going to give us sine and cosine. So we're going to get C4 times the cosine of 2t plus C5 times the sine of 2t. So that's what that one's going to look like. Now it's just a matter of figuring out what the C's are. All right, well, this is where we're going to make use of our initial conditions. So we got to start by getting some derivatives. Luckily, this is pretty fast. And hopefully I don't make any mistakes. If I do, Ralph will catch them and tell you all about it. I like having Ralph. You're really useful here in catching my issues. All right, so there's y prime, y double prime, so 2c3 minus 4c4 cosine of 2t plus no minus 4c5 sine. All right, so we just got to get 2 more here. So the third derivative, now that first c is gone, we now have a plus 8 c4 cosine of 2t minus 8c5.
The first one should be sine.
Yep, thank you. I caught that as soon as I wrote the other one as a cosine. Okay, so then lastly, I think we're going to be good now. Famous last words. 16 c4 cosine of 2t plus 16 c5 sine of 2t. Okay, so here are all our derivatives. So now we can plug in our zeros. I'm going to actually start at the bottom. So when I plug 0 in down here, I'm going to get 1 equals, well, the cosine of 0 is 1. So 16c4. And the sine of 0 is 0. So that's what that one gives me. So that tells me that C4 is 1/16. So we'll go ahead and put a 1/16 there. So then for the y triple prime, that minus 1 is going to equal, well, now the sine of 0 is 0. So that goes Of course. Of course. Oh wait, I'm back up. Okay, I'm back. I'm back. I'm gonna leave my other one on my phone on just in case, so I can hop back on there. I don't get it. I completely don't get it because my computer and my phone are both on the same Wi-Fi network. In fact, uh, so maybe it is just because it's Wednesdays. All right. And I knew this was going to happen. So all that work that I just did is gone from the whiteboard. But anyway, C1 was 31/16. C2 was 23/4. C3 was 5/8. Hopefully you guys saw C4 and C5. C4 was 1/16 and C5 was 1/8. Anyway, so hopefully at least what you got from that was that we're not doing anything different. It's still the same old, same old. It's just more because it's, you know, a greater degree, right? It's a bigger deal. All right, so how are you guys feeling about doing a homogeneous constant coefficient?
Not bad, except
Yeah.
depending on the order, it's going to be a little messy.
Okay. Yeah, and they can get long, right? And like you're saying, depending on the order, they can be extremely long. But at least the process is the process. And don't hesitate to use your technology to help you find the solutions to the polynomial. All right, I think I froze there, but I think I'm back. All right, okay, so that's for homogeneous. So then what if they're non-homogeneous? Well, let's start by just kind of reminding ourselves what techniques we had for second order. So one of the techniques that we did was the undetermined coefficients. That was the one where we make a guess. So we looked at the form. Trig functions or combinations thereof, right? So that was one of the things that we did. Do you remember the other things we did to try to find the particular solution?
Reduction of order.
Okay, so we had reduction of order. And what did you need to do reduction of order?
You needed one of the solutions to the homogeneous, or was it just in general?
So you know you do need something from the fundamental set. Or yeah, so we do need a solution. Okay, so if you know one of the fundamental set, that's good enough to reduce your order down. It's kind of like if you know one of the roots to the polynomial, you can divide it out. And now you've got a polynomial that's 1 degree less. So it's kind of the same idea there. Now, that was the second thing we did. And then you guys remember the other one we did?
Variation of parameters.
Yeah, that was the name of it. It was variation of parameters. And what was that one?
You remember that everyone hated it.
You need two solutions.
Okay, so yeah, so this one, it wasn't, well, it was, we needed two solutions before, but that was because it was second order. This one, you actually need the entire fundamental set. So Jesus, you were right for when we did that. For the second order, we needed two solutions because that was the entire fundamental set. But now if we're going to extend ourselves, it's better to think of it as we need all of them. And then Victor, you're also right that most people did not like that one. So what do you do if you have the entire fundamental set? What do you do with the variation of parameters?
I think you used the Wronskian, but I don't honestly remember.
All right, can you say that again?
I said I think you used the Wronskian, but I don't quite remember.
Okay. Yeah, it's funny. I heard it really muffled through my phone, but not through my ear. But yeah, no, that's exactly what we do. We create the Wronskian. And then we find its inverse. And that's where we took the inverse of the matrix and then we multiplied it by something that had a whole bunch of zeros and the function that non-homogeneous. We had these three methods. Okay, so what are the methods that we're going to have if we're higher order non-homogeneous?
I'm guessing it's going to be the same, just bigger.
Yep. And that's exactly it. If we know the entire fundamental set, so I can tell that I'm frozen. So let me come to my phone. But if we know one of them, we can use that one and then reduce the order. All right, so we can do that. Or if we, hold on a second, I'm gonna start my video just so you guys see me and you're not just listening to a face or yeah, my picture. Anyway, so if you know the entire set, fundamental set, you can do variation of parameters. If you know just one of them, you can use that to reduce the order. That's especially, reducing order is especially good if you've got a third order, right? Because if you have a third order and you get one solution, it now becomes a second order and oh, we're home free. We know exactly what to do. And then the other option is that if the homogeneous or the non-homogeneous part is a nice function, trig function, an exponential polynomial, we can do undetermined coefficients. We can make our guess and then see how it pans out. Okay, so again, really good news. Nothing changes. We're still going to do the exact same things. It's just, well, like Bradley said, bigger. All right, so I'll tell you what I'm going to do because it looks like my computer does not want to connect. So I'm going to leave that off. We're just going to go with my phone here. So I'm going to hop up to my whiteboard. So give me a second here because I want to show you a couple of examples using the method of undetermined coefficients where we're making our guess and going from there. All right, so give me a second here. I'm gonna have to untangle my cords. You're gonna be able to see more of the room and the mess that it is, although it's not terrible, but anyway, so hold tight, we'll get this set up. Ooh, parametrics.
It's upside down.
I upside down.
Yeah.
Oh my god. Let's see if I can fake my phone into thinking that I'm right side up again. Hey, I'm over on my right side up. Okay. Anyway. I am convinced that the universe wants this class over. Are you guys getting that impression?
Yep.
So, all right. Now I'm all flummoxed. I love it. All right, well let's do this thing.
I have a
Alright.
question for you, real quick.
Yeah, go for it.
Are Laplace transforms known for higher order derivatives?
Yes.
Okay.
Yeah, you know how we you have the one for the second order,
Yeah.
for the second derivative where you got the s squared times the Laplace transform and then the minus s times and so on. That pattern actually continues. So if you have, say, a fourth derivative, the Laplace transform of that is going to be s to the fourth times the Laplace transform of y minus, then you're going to get s cubed times the third derivative of 0 and then minus s squared times the second derivative and so on down the line. So if you look on the table of Laplace transforms, there is one that shows a generic nth derivative.
Yeah, it's at the very bottom of the table, I think.
Yeah. So so yeah, even think about that. So like the whole Laplace transform idea, yeah, you can apply that to these higher order. You want to do series solutions? Again, I know you don't want to, but if series solutions was something that was worth attempting, yeah, you can do that for the higher orders as well. Again, it just means more, right? There's just more, but it's the same steps every time. And so that really is the beauty of this higher order stuff, is that it doesn't actually, it doesn't change the process really. There's going to be a slight change of process for the variation of parameters that we'll talk about next time. But beyond that doesn't really change much. Okay, so let's actually do one of these undetermined coefficients. Let's say we've got y triple prime plus y double prime equals cosine of 2t. And this is good review for doing the undetermined coefficients anyway, because it's been a while. Yeah, it's funny. So Ralph, you were saying it's been a while since I've been on the whiteboard in this class. That's one of the reasons is the glare. So I just turned on the light, tried to get better light on this, and I got horrible reflection. So anyway, and yet we continue. All right, so think about what do we do. So with this, where we're going to make a guess. What's the very first thing that you do?
Homogeneous?
Yeah, we find the solution to the homogeneous first. So in this case, this is going to be r cubed. The polynomial we need to solve is r cubed plus r squared equals 0. So we get r equals 0 and r equals -1. So our solutions are going to be 1 from the 0. It's repeated, so the second one is t. And then the -1 gives us e to the minus t. So here is a fundamental set of solutions to the homogeneous.
Why is it not a C1? Why is it just a normal one?
It will be a C1 when I put it together, right? When we actually form our solution, we write C1 times Y1 plus C2 times Y2 plus C3 times Y3. And that's when it'll turn into a C1. I could use any constant. I'm just choosing one because one's an easy constant. Does that make sense?
Yeah.
Okay. All right, so that takes care of our homogeneous. But now we got to get our particular. So this is where we make our guess. So since it's cosine of 2t, we're going to go with that our particular guess is going to be A cosine of 2t plus B sine of 2t. And now we need to differentiate. And heaven help me. Okay, so I think I got them. I've realized that one of the reasons I have trouble with these is because as I'm talking and writing, there's a little bit of a delay. And so sometimes I'm thinking one thing but saying another and then writing a third. And at least that's the excuse I'm going to go with. Sounds plausible, right? Better than I'm getting old and I can't do calculus anymore. I don't like the thought of that. All right, so let's take these and put them into the differential equation. So we're taking the third derivative plus the second derivative. So if we combine those, and I'm going to group them by types, sine and cosine, we're going to get 8a minus 4b times the sine of 2t plus negative 4a minus 8b times the cosine of 2t. And we need that to equal cosine of 2t. So that gives us 8a minus 4b equals 1, or sorry, 0. There are no signs. And then minus 4a minus 8b equals 1. Okay, so nice, easy system to go ahead and solve. And I believe that this gives us a equals 1/20th. No, minus 1/20th. And then b is equal to minus 1/10. He says very unsure of himself, but no, that looks like that's right. All right, so that's then going to give us what our particular solution looks like. So if I put that all together, we get that y equals C1 plus C2t plus C3 e to the minus t minus 1/20th cosine of 2t minus 1/10 sine of 2t. And so there's our solution. All right, so notice that the process isn't any different. Really, the only thing that changed, two things, right? The one was, of course, bigger polynomial, so more roots. But when it came to our guess, it just meant we had to go further down with our derivatives. So I actually chalk that up to, I mean, I classify that as good news again. It's like, okay, it's the same thing. It's just more. All right, let me show you another one. We're not going to go all the way through it because by this point, nobody wants to do all the derivatives. Nobody cares about it. You definitely don't want to watch me do it. But I want to do this next one, at least get it set up for what our guess looks like. Because you may recall that there are times where our guess, we have to amend it a little bit. And I want to just kind of remind you about that and see how it changes a little bit when we go higher order. But before we go there, any questions before I erase this thing?
I have a question. I don't know why I never asked this before, but I've always been curious as to why we add the sign as well. Like it's cosine of 2t, that's what it's equal to, but our guess is a cosine 2t plus b sine of 2t. I've always been curious why we add the extra trig function.
Why both are there?
Yeah.
Okay. That's because when you differentiate, the one becomes the other, right? Like think about sine. You differentiate, it becomes cosine. You differentiate, it becomes sine again. Obviously with different pluses or minuses. So in this situation, like if what we're looking for is a cosine of 2t, that cosine can actually show up from sines, depending upon the derivatives, right? Like just think about sine itself. If y equals sine, then the first derivative has cosine, so does the third, so does the fifth, so does the seventh, and so on. And so like this guy right here, this y to this third derivative, that tells me that if I start with sine, I could get cosine. So does that make sense?
Yes.
Okay. So it's just because of the fact that the one turns into the other. And so since we have all manner of possible derivatives in here, we just go with the, let's just assume they're both part of it and go from there. All right, so let's just do one more here and then we'll call it a day before my phone decides to crap out on me or I get some phone call or something. All right, so let's try this. Let's say we've got the fourth derivative plus 2 times the third derivative plus the second derivative. And this is going to equal 16 minus e to the minus t. All right, so again, we're going to just see if we can get the solution to this. Like I said, we're not going to go all the way through, but we'll at least get ourselves to the what our guess should look like. So we create our polynomial. R to the fourth plus 2r cubed plus r squared equals 0. Factor out the r squared. R squared plus 2r plus 1, that also factors to r plus 1 squared. So we get r equals 0 and r equals minus 1. So in terms of our fundamental set, we're going to have y1 equals 1. The 0 is repeated, so that means y2 is equal to t. Y3 is going to be e to the minus t, to the minus 1, but it's also repeated, which gives us t e to the minus t. So there is a fundamental set of solutions. Now we come over here and we go to make our guess for our particular, and we see that we have a constant. We got the 16. All right, so that would suggest that we guess a constant. However, it can't be a constant because that's fundamental, part of the fundamental set. So what we need to do is multiply it by t. Right, so we thought constant, but we go, nope, we need a t. But that is also in the fundamental set. So what do?
Multiply by t again.
By another t. So we're actually going to go with t squared times that constant. So in terms of what might actually make our 16, we're going to go with t squared times that. All right. So then we go to the e to the minus t. Same kind of story. Right? We go, okay, I want to b times e to the minus t. But you go, oh, no, e to the minus t is part of that. So I need to put a t on it. Oh, no, t e to the minus t is part of it. So I got to put a t squared on it. So this is the kind of thing that's going to happen now that we're in higher order. We're going to have to end up multiplying by more than just t. Sometimes. Right? Sometimes we're going to have to multiply by t squared, t cubed, t to the fourth. This depends on how frequently those things continue to show up. All right, so hopefully you guys are feeling pretty good about this. You're like, all right, nothing new, just more. And we'll see that that continues. What we're going to do next time is, all right, let's look at variation of parameters because there is a slight little tweak to it. It's very minor, very minor. But the variation of parameters you guys already didn't really care for. So it's probably going to be good to see that again anyway. All right. So I think I'm going to stop here. I don't think I'm going to stop here. I am going to stop here. And we'll pick this up on Friday. All right. So again, apologize for the technical difficulties. 2 more weeks. We can do this. 2 more weeks. I'm telling myself. All right.
It's the
So with
final
that,
countdown.
yeah, right. Okay. So with that, you guys have an awesome couple of days, and I'll see y'all on Friday.